before we can move on to the inferential statistics of chapters 9, 10, 11, and so on, we need to establish the sampling distribution for one other important statistic and parameter combo, and that is for proportions. So imagine that you have a population proportion. So, for example, the proportion of all the people in the US that are going to give away Halloween candy this year. All right, that's a population value. So you'd have to call up every single person in the US and find out whether they're giving away Halloween candy this year. Well, that would take a really long time, so that's not going to work. What you could do instead is call up a sample of people and get the proportion from them and say, hey, are you going to give away Halloween candy this year? And so a certain number of them, let's say 700 of them say yes, out of 1,000. That would give you a p hat with 700 on the top, 1,000 on the bottom, and that would give you a percentage. And you'd say 70% of people say yes, and that's a p hat. Notice what I'm saying, p hat. It has a little hat on its head, right? So it's p hat. It's the sample proportion. X is the number that has the characteristic you want, N is the total sample size. Okay, so we're going to experiment with this just a little bit. I have a coin in my hands, you can't see it, and I'm going to toss this coin 5 times and record the number of heads that I get. 2, 2. So I got 2 heads out of 5. So my sample size for me was 5. Now you could take your own coin and do it yourself if you so desire. Now I have a sample proportion from that p hat. So let me write that out. P hat is equal to X over N. Now, N. I flipped it 5 times, so my denominator is 5. And my numerator is 2 because I got 2 heads in my 5 tosses. All right, 2 out of 5 makes 0.4. So my proportion is 0.4, which is also 40%. Of course, we never really write it as 40% very often. Now, this should look familiar to you because you kind of saw this idea of fractions versus decimals versus percentages in Chapter 5 in probability. The one we use the most often will be the decimal. Not that the other two are invalid, it's just they're not as useful as the decimal. Now, the real question is, what is the population proportion? Now, here is one case where I actually do know the population proportion. The population proportion is 0.5. Because it's a coin, and you're just going to have to believe me, it's a fair coin. I'm sitting here with this coin in my hand. It's not weighted, and that means that I have a 50-50 shot of getting heads, which means 0.5. All right, or 1 out of 2, I guess, if I wanted to do the fraction in there as well, just for fun. So any of those would be valid, either the 1/2, the 0.5, or the 50%. So now I'm going to construct a frequency distribution and histogram of the proportion of heads from our class. So I did this with a classroom full of students. You'll just have to trust me. And the numbers they reached were 1, 4, 5, 9, 7, and 2. And we want to make a histogram of that. So you're going to have to draw your bars. The first one goes to 1, the second one goes to 4, and so on. So I'm going to do that with the computer, and I'll be right back. There we have the graph. You can see I made it so the bars touch because this is a histogram. So I have those there, and you can see this kind of has a little bit of a skewed left distribution for this particular class that I did. Some of my other classes were more symmetric, but this one was skewed left. Just a little bit. All right. So what this is leading us to is the idea of, if I take this sample of so many tosses, and then I do it again, and another sample of so many tosses, another sample of so many tosses, the question is, how do those samples relate to each other? How do they vary from sample to sample? And what kind of shape would they have? And that is where the central limit theorem for proportions comes in. So you already know the central limit theorem for sample means. This is for sample proportions. Suppose there is a sample of size n taken from a population with a population proportion p, such that the following conditions are met. 1, it has to be a random sample with independence, and just like before we saw You can either collect with or without replacement, but if you do without replacement, then you have to kind of look at condition 3. So those two kind of go together. So it's saying, look, it needs to be random, which of course a coin toss is easy to be random, but it has to be random even when you're calling people up to ask them whether they're giving away Halloween candy this year. It has to be a random group that you're going to, not just all people in the same neighborhood or all people in the same city, for example. All right, so if you do it without replacement. With replacement's no trouble to get independence. I mean, independence and with replacement go together. But if you're going to do it without replacement, that's fine as long as it's part of a large population. So as long as your little scoop, your little sample is less than 5% of the population, then you're okay. Because yes, you're affecting what's left, but not, you're affecting it so minimally by taking such a small sample in relation to the whole that it's fine. So in other words, we want a large sample, which we'll talk about in 2, but not too big. And that's condition 3. So you want a big sample, but not too big. You want to be like Goldilocks. You want to be just right. All right, now the other thing we need is a large sample. So a large sample means we need it to ensure normality. Now in the central limit theorem for means, let me go back, it's a bit back here. Oh, there it was. Central limit theorem for means, we said we had to have n greater than 30. That's what was going to be large enough, quote unquote. But for proportions, oh, and by the way, you are allowed to know that it was normal to begin with sometimes for means. But for proportions, that's not going to happen. For proportions, you're always going to have to check that n times p times 1 minus p is greater than or equal to 10. It cannot be given to you in the problem like it was for means, and 30 is not a big enough number. It's going to be bigger than that. It has to be that n times p times 1 minus p is greater than 10. If you have those 3 cases, it's random and independent. And to make sure independence happens, you make sure you have a big population, and then you have a large enough sample to ensure normality, which is that second one. Then these 3 things are going to occur. You're going to have the distribution of sample proportions is going to have a normal distribution. And again, that normal distribution is tied to condition number 2 in particular, right? So you want to make sure that you have that condition 2 met, okay? Then the center will be the mu of the p hats, which will be p, and the standard error is the standard deviation of the sampling distribution of sample proportions. Boy, say that 10 times fast. Is called the standard error of the proportion, and it's abbreviated SE of p hat, which is equal to sigma p hat, which is the square root of p times 1 minus p over n. So it's very similar, all of this, to the central limit theorem for means, but this is for proportions now. So you have p hats instead of x bars. The normal distribution is a little bit harder to come by. You'll have to double check that condition 2 up there. And then the standard error is SE of p hat. So according to central limit theorem, what is the mean of our sampling distribution for 5 coin tosses? All right, so technically we don't have condition 2 met for ours, but that's okay, we'll just pretend. So that'd be n times p times 1 minus, the central limit theorem, the mean. The mean would be p, so that'd be mu of p hat, which is equal to 0.5. That was p. Yeah, p, which is 0.5. There we go. All right, that's fine. Now what about the standard error? What's the spread? The standard deviation of the sampling distribution of p hat, I should say, of p hat. For those 5 coin tosses. Well, that would be this formula right here. So let me bring this down. There I clicked in the formula here. So let's see here. P was 0.5, 1 minus 0.5 over n, which was 5 tosses. So let's see. Let's go grab a calculator. Second square root. Now, if you have the 84, you can actually do alpha F1, pick number 1, and make it a fraction in there. So that might be easier for you to see. 0.5, 1 minus 0.5. Then use your arrow key to get down, and then say 5. and it's 0.2236. Again, technically we didn't meet all the conditions. We met the independence part and the random part, but we didn't really meet the normal distribution part, but that's okay. That's why when we did it, this didn't turn out to be a normal distribution right here, but we're just pretending. So there we go. All right, now what would happen to our shape if we did 50 tosses or 100 tosses? What would happen? So let's check. It would be normal, right? Because n times p, let's do it. Let's pretend we're doing 50 tosses. So if we say n equals 50, we'd say 50 times 1, or 0.5, 0.5 times 1 minus 0.5. Okay, let me grab the calculator. 50 times 0.5 times, parentheses, 1 minus 0.5 is 12.5, which is greater than 10. Yay, right? We want it to be greater than 10. If it's not greater than 10, then we don't have normal. Just on a side note, for the one we did with only 5 tosses, it wasn't normal. Again, that's why our distribution didn't work out nicely when we graphed it. So if I delete this 0 and I do it, 5 times that, see, I only get 1.25. That's not bigger than 10. That's why I wasn't guaranteed a normal distribution. Oh, one other thing I want to say here, 23607. Here you actually want to keep more decimal places, so we better make a note. So note, keep 6 decimal places at least. And my math lab wants you to do that as well. Keep at least 6 decimal places for the standard error of the p hat. Okay. There we go. Keep at least 6 decimal places. Otherwise, we're going to lose accuracy. All right, so now what would it be for p? This would be 0.5 still. That would be your center because p is 0.5. And then now SE of p hat, well, that's what we were just doing. But instead of 5 in that denominator, we would let that get larger to like 50, say. So let me do that. So there it is. I put the numbers in. 0.5, 1 minus 0.5 over 50. So let me grab the calculator. And I could use that fraction button again, but I'll show you how to do it without the fraction. So if you second square root, 0.5, parentheses, 1 minus 0.5, close your parentheses, divided by, instead of 5, I'm going to divide it by 50. And I get 0.070711. So you want to keep at least 6 decimal places. I just clicked over there, 070711. At least 6, if not more. Here we go. So make a note. As n gets larger, spread gets smaller. And shape becomes more and more normal. It's more and more normal, but with a smaller shape, or a smaller spread. There, and I just bolded that and put it right there. All right. And it makes a certain kind of sense because n is in your denominator, right? So if you make your denominator bigger, to a bigger number, like 50, then it's going to make your overall spread get smaller. The bigger that number is, the smaller that spread is. So for example, let me just show you what it would be like if I had, well, let me do 500 since I just had 500 in there accidentally. You can see it makes it smaller from 0.07 to 0.02, right? And again, we always keep 6 decimal places. Keep 6 decimal places. Let me highlight that one because that's a big deal. Okay, we set it there and we're saying it right here. Keep 6 decimal places for the standard error. And then this little note right here, as n gets larger, your spread gets smaller, but the curve becomes more and more normal and your center stays the same. Center is always at your p-value, which is 0.5 in this particular example.